Hey there, in this video I want to describe the PySpace notation and how you can model the particle in the wave and force using what I call the momentum shell. In this simple example, um, I have the PySpace notation here, which is the stationary object. You have an object traveling at, say, 0.8 of the speed of light, and this is the area loss. And then this is the size of the pi shell of the rocket, which is 0.6. This is obtained using the Lorentz-Fitzgerald transformation. So what that tells you is that 0.8 is the amount of area loss on the observer pi shell, and 0.6 is the size that the rocket remains at. If we embed one in the other, we get a rocket with with a momentum shell around it in blue, and the blue area is the um, yellow minus the red, giving us this blue area here. And now in terms of actual force, the in here this area here is where the waves exist, and this is the particle. So the waves are in here, the momentum shell waves are in here, and this is the particle. So this is a way of visualizing these concepts in physics using the pi shell notation. Then there's de Broglie, and he showed there's a wavelength relationship between motion and Planck's constant, which is the h over p or h over mv. And if we wanted to draw that, we get the following. We get basically here, we get again the stationary object, the area loss in the rocket. This is your momentum pi shell, and in here is in this momentum pi shell is hf, which is your momentum waves, and also is also the MV side of it. The HF is the quantized space that the waves live in, so the HF is equal to the MV, so you can solve for the wavelength. Now, in terms of actually what do the wavelengths look like, it's been shown through various experiments that you can calculate with a baseball, for example, has a wavelength of 1.1 by 10 to the minus 34 if it weighs 0.15 kilos and 40 meters per second of velocity, and so on. But how does it look like in PySpace? How do you visualize it? So in PySpace, the way you visualize the momentum shell, or the waves within the momentum shell, you visualize them as a wave within a wave, and the outer wave, which is the sine x here, is the velocity component, and the sine 10x here is it, like that indicates mass of say 10, and it's carried. So one wave carries the other wave. So the mass is carried, as in the PySpace theory, the mass waves are said to be carried non-locally. If you're not sure about what that means, you just have to read up on the theory a little bit more. If I go up to the beginning of the document is called it's available on the PySpace theory website, and it's called the particle, the wave, and the momentum shell. So that's how you'll get it. I'll show you that in a minute. But there's a bunch of diagrams. But we start out with the idea of a particle. We start out with the idea of the stationary object, the area loss, and the rocket, and then we end up with the concept of the particle and the wave. And then what we evolve in the document is the idea that this section of area here is actually the momentum shell, and this helps guide and remember the direction that the pi shell wants to move in. Now, in terms of actually the contents of the document, it's a couple of pages long, and it describes how the de Broglie hypothesis works, how to model force and the momentum shell, and it also shows how to model the momentum wave and the compression wave. You can get the document from the PySpace website. There's a HTML version of it, and there's also a PDF version of it. The website is here. It may change over time, but at the time of recording, that's where it is. If you search for it, you should be able to find it. And this is known as the PySpace physics theory. And one of the aspects of it is, apart from the software modeling, I'm going to put in this ability to visualize special relativity and things like that. In this case, I was covering the momentum aspect of physics. Thanks very much. That's it.